Hi folks, this is Maria, and today we're going to be talking about proton transfer, specifically when we're talking about acids and bases. So the goals of this video are just to review some of the introductory acid-base concepts that you talked about in class last week, and to discuss what an acid or base actually does in solution. We're also going to talk about something called conjugate acids and bases, and that might seem unusual right now. Don't worry, we will go over it in just a bit. Alright, so the first thing that you kind of learned from class when you're going through is just how do you actually identify an acid or a base from their formula. And for acids, when we're talking about them, the two biggest things are acids will have hydrogen somewhere in their formula, and most are covalent molecules, according to the rules that you've learned in this class. Although they're covalent molecules, if you remember back to when we were doing covalent versus ionic compounds, acids will still conduct in water. It's an exception to a lot of those covalent molecules rules. This comes from, crazy enough, the hydrogen that's in their formula. We'll talk more about that in a sec. So some examples: hydrochloric acid, sulfuric acid, hydrobromic acid, acetic acid, citric acid. For bases, most of the bases we use in this class will have either a hydroxide ion, a carbonate ion, or a bicarbonate ion. Those are pretty big giveaways. This means most of the bases we use in this class are ionic compounds. The only exception that you really need to know well is ammonia, which is NH3. So that is also a base, but obviously it is not an ionic compound. But we'll talk about what makes it a base in just a second. So some of the examples of things that you should know right away just from their formula that they're a base: things like sodium carbonate, sodium hydroxide, potassium hydroxide, sodium bicarbonate, magnesium hydroxide, lots of things like that. Okay, so we talked about two weird exceptions in class last week, or if you haven't talked about it yet, you will talk about it more. So ammonia is a base, but it is a covalent compound, and methanol is, so CH3OH is an acid, even though it has what looks like it's a hydroxide group in there. Okay, so how do we actually know that? Well, the best way to kind of think about it is acids are defined as a molecule that donates its proton or protons, while bases are defined as compounds that are good at accepting protons. The reason I have multiple S's is it depends on what the acid or the base is. It can sometimes accept more or donate more than one proton at a time. Now, what do I mean when I'm saying a proton? That's actually the exact same thing as a hydrogen ion. It's a common term that we use in both chemistry and biology. Remember that if I had a hydrogen atom is composed of one proton and one electron. So once it loses that electron, it's left with just a proton. And so that's why we use this interchangeably when we're talking about H+ ions. Okay, so let's talk about acids reacting with water, and we're just going to walk through a few different examples, and then at the end I'm going to remind you of kind of what you might see that's similar throughout. Alright, so if I look at hydrochloric acid reacting with water, so that going through, reacting with water. Okay, so you see this kind of funny molecule right here. So pay attention, you kind of see that both things end up being charged on the other side. That makes sense, because technically this hydrogen was lost from hydrochloric acid, and another hydrogen was added to water. Okay, so looking at sulfuric acid with water. So if I look at that, I end up seeing that the sulfate ion ends up being separated out, and then I have two of these H3O+ ions as well. Again, the sulfuric acid lost its protons. Okay, here's nitric acid. And here is methanol. So that was one that was a kind of funny one for when you were looking at this in class. Okay, so take a moment, what's the similarities between all these reactions? All right, so of course you probably noticed this right away, that funny H3O plus thing. So it's an ion that's called hydronium, and the more hydronium in solution, the more acidic that solution is. For a few different reasons, chemists and biologists often just shorten it to H+. That's what we end up doing a lot of time. It's usually easier if you have an acid reacting with water to write out the hydronium, but in most other cases, you don't actually end up writing it out. So just something interesting to note. All right, let's talk about bases with water. So here's our famous sodium hydroxide reacting with water. Okay, you'll just notice a few things. Here's sodium carbonate reacting with water. You might notice a few things there as well. Sodium bicarbonate reacting with water. And then ammonia reacting with water. Okay, so if you're going through, just take a moment. What's something that's similar in every single one of these reactions? Just take a look through. So of course, you identify that the hydroxide ion is present. This is a stereotypical thing of a base reacting with water. The more, when a base is reacting with water, hydroxide will become present in the solution. And the more hydroxide present in solution, the more basic the solution is. There is one other thing I want to note. There's been a few of these kind of funny arrows, and it's been part of why Becky and myself have, ever since you've been drawing chemical arrows in this class, we've been like, you cannot use equal signs. And the reason why is actually because of arrows like these. Sometimes reactions don't go completely what we call forwards. So this would be an example of one where it goes completely forwards. Sometimes reactions are capable of going both forwards and backwards. So what I mean by that is really just reactants can become products, products can become reactants. You don't really need to know when to use this arrow. That's not something that we're going to ask you to do. We just still ask, please don't use the equal signs for an arrow. All right, so at this point, you've seen water, where it was technically acting as a base, and water, where it was technically acting as an acid. So what is kind of interesting at this point is usually people are like, hold on, but isn't water like a neutral compound? You're right. Water is an amphoteric molecule. It can act as either an acid or a base, and that's literally the only one that we'll use in this class. Okay, so let's talk about the conjugate acid base thing. So I think this is just a great diagram to take a look at. So when we're talking about conjugates, acids, and bases, the first thing is, of course, always identify what your acid is and what your base is. So it makes sense in this case, when I'm looking at it, this is the one that ends up losing a proton. So since it loses a proton, this must be my acid. This water here is what ends up gaining a proton. And so that's why it is acting as a base in this particular case. Remember, water, it could act as a base or it could act as an acid. So if that's true, and we look at this, and so it looks like the base is then paired with this conjugate acid. So the conjugate acid, if I look at this, it's essentially the one that gained the proton. And the conjugate base, it's the one that lost the proton. So if you're looking for definitions, it's a little funky, I know, and it just takes some practice and just takes a little time to get used to it. But the conjugate acid is the molecule that was the base, but accepted the protons. So if we're looking at this here, so the molecule that was the base, so here's my base, but it accepted protons. So that's why this is my conjugate acid. You can essentially describe it as base plus H. The conjugate base is the molecule that was the acid, but donated its protons. So this was the acid, but it lost its protons, so that's why this would be my conjugate base here. So essentially, it's acid minus H. As I said, it'll just take a little practice to get used to this. Okay, before we go into that practice, though, I do want to refresh your memory on neutralization reactions. We've talked about them before because they're essentially a type of double replacement reaction. It's where I have an acid reacting with a base, and generally both have to be strong when we're talking about them in this class. It'll create a salt, and it always will create water. So here's some examples. If I have sodium hydroxide reacting with hydrochloric acid, I end up creating water and sodium chloride. Just something to remember. This essentially can be translated, if you're thinking about this in solution, of what's actually happening. The sodium hydroxide breaks up into pieces in solution, and because this is a strong acid, this also technically breaks up into pieces, even though we know this is a covalent compound, but that's kind of the funkiness about it being an acid as well. So this can essentially be translated as all this stuff is broken apart in solution. All right, here's sulfuric acid reacting with potassium hydroxide. Again, I form water and I form potassium sulfate. Okay, so let's just walk through a little practice. After I press for each one, just wait it and pause, see if you can predict what's the conjugate acid, what's the conjugate base, what's the acid, what's the base, and kind of test yourself as I go through. All right, so I'm going to pick on the one from the last slide. So sodium hydroxide plus hydrochloric acid. So it produces water and sodium chloride. So take a moment, pause, see if you can identify what's the acid, what's the base, and what's the conjugate acid, and what's the conjugate base. All right, so here's the base is just the hydroxide from the NaOH. The acid is the H plus from the hydrochloric acid. The conjugate acid in this case is water, and the conjugate base from this case is actually the chloride, because that's what lost the proton. Okay, another neutralization reaction from the first page. Okay, and then the base is again the hydroxide ion, the acid is protons from sulfuric acid, conjugate acid water, conjugate base is the sulfate ion in this case. All right. And then, and if that confuses you, definitely write that down. See if you can go over things with your teacher. You'll definitely go over that with your teacher. All right, here's nitric acid reacting with water. So pause, see if you can predict. Okay. So in this particular case, water is what's actually acting as the base. The reason I know that water ends up acting as a base here, well, is because kind of what actually ends up forming. So it kind of helps to see that when going through. And also when I'm reacting with a very strong acid, well, water's like definitely a better base than nitric acid. So it's not a great base, but it is a base in this situation. All right. And you'll see that the conjugate acid that ends up forming in this particular case is the hydronium ion, and the conjugate base is the nitrate ion. All right, this one I know always confuses people because it's when we're looking at lithium hydroxide in water, and anytime we have one of the ones where it's water, this one's a little funky. So pause, see if you can predict. All right, so the base, the hydroxide ion, the acid is water. The conjugate acid, in this case, is technically from here, this hydroxide ion accepted one of the protons from the water, so, well, but it ends up forming water again. So I end up with conjugate acid of water and the conjugate base of hydroxide. Interesting, right? All right. The practice problems in this case are a little funky. But again, go through, identify the acid, the base, the conjugate acid, and the conjugate base. And you gotta do that for full credit. Definitely write down any questions on anything you're confused of and ask your teacher in class during the discussion for the next time that you see us. All right. Well, have a great day, and we'll see you soon.